this screencast is to calculate the steady state error for a unit step input, and then to follow that up with the steady state error for a unit ramp input, two different parts. Okay. Well, we've talked about this before, that if you have a control system that has this structure, we've talked about identifying the type of the system, and we see here in the forward loop there's a free S, okay, a free S at the origin, and so because there's this pole at the origin, this is going to be a type 1 system. And for a type 1 system, the steady state error is 0. Okay, so the steady state error for a unit step is 0. Okay, so we can actually do that one by inspection. The answer here is 0. Okay, so let's move on to the unit ramp. All right, what I'm expecting you to know is that the Laplace transform of the error signal is going to be R over 1 plus GH. Okay, and so I didn't put R. Let's just erase that and just call that R. Okay, so we need to identify G and H. Okay, so G would be the top part here and here, and H is in the feedback path here. Okay, so we can write this out that E steady state is going to be the limit as S goes to 0 of S times R of S, but because we're in a ramp, R of S is 1 over S squared. Okay, and then 1 plus GH. Okay, so when I write down GH, that would be S plus 1 over S times 2 S plus 1 times S plus 2 over S plus 1 squared plus 1 squared. Okay, so notice what happens here is that this S cancels with one of these, and then this S essentially shows up, it's algebraically equivalent to put it in the denominator. Okay, so notice what happens at that point. You don't have to do a lot of algebra. You can look at this and you can say, all right, this S is going to distribute through. I'll get an S term here, and then it will cancel with that S, and I will get S plus 1, 2S plus 1, S plus 2, all over S plus 1 squared plus 1 squared. Okay. So because that canceled, this is no longer going to have an infinity term in it. Okay, so we plug in S equals 0, and what I end up with is a 1, and then for this you get 0 plus, and you plug into this term, just plugging in for all the S's, and on the top you'd get 1 times 1 times 2 divided by 1 squared plus 1 squared. Okay, so doing the math on that, 2 over 2 is 1, and so the steady state error would be 1 in this case. So you might wonder what that even means. All right, so if you look at steady state error for a ramp, okay, here's the reference input. It's a ramp. So what we know is that our output's going to do something, and it's eventually going to sort of track, right, where there's a difference between the reference input and the real input. Okay, so this distance here, this vertical distance, is the steady state error. Okay, it's the reference, this is the reference signal minus the output signal.